Hey guys, welcome to your next tutorial. Today what we're going to be doing is going over shaders some more. We're going to learn a few more things about the shaders that we haven't learned yet. For instance, we're going to make it so that we can change the color and we can change color over time too and just make a lot of really cool effects and some trippy effects. But right off the bat, one thing I want to do, or two things I want to do, is show you two bugs that we had in the previous tutorials that we definitely need to fix. If you go to GLSL program and go down to link shaders, here you'll see we create the program ID here. Instead, we actually want to cut that out of there and put it at the top of compile shaders. And the reason we want to do that is because this program ID needs to be created whenever we call add attribute. However, since we call add attribute before link shaders, we were calling glbind attribute location with a program ID of 0. Now that results in this not doing anything at all. So basically we didn't bind any attributes to our shader. The reason it still worked is because OpenGL will automatically bind the attribute locations for you. It'll basically guess if you don't set them yourselves, but we don't want it to do that. We want to manually set these. So just fix that little bug and then everything should work perfectly fine. The next bug is in errors.cpp in this fatal error function. I told you that SDL quits the game. It actually does not quit the game. It just quits all the SDL systems that we initialized with SDL init. To actually quit the game, we need to include C standard. No, it's stdlib. No, it is cstdlib, yes. C standard library. And then after SDL quit, we want to type exit. And then inside this, we can put a code, like when we were in int main, whenever we would like return a random error code, that's basically the same thing. We can type any number in here, just make it something that's not 0, because 0 usually means everything was okay. So I'm going to return 69 there, and then I'm going to put a semicolon. So now this is properly going to call SDL quit to shut down SDL, and then it will actually exit the game so it doesn't keep running and cause us other errors. Alright, so that's that. Now what we want to do is we want to enhance our shaders. So let's go ahead and run it and see what it looks like right now so we can kind of get a refresher on what we've been doing so far. And we should get basically just a quad in the bottom left hand corner if this thing ever compiles. And while it's figuring out how to compile, let's come down here and I want to make the sprite bigger. So here we have a red box in the bottom left hand corner. I want to actually cover the entire background of the screen with the box. So to do that, we're just going to change the width and the height to be 2. Because remember, this is 2. 2 is the width of the normalized device coordinates. So there, now the whole background is red. So now we can make a lot of really cool effects and play around with this. All right, so one thing I think we should do is we should add in color here in the vertex shader. So now instead of just sending a vertex position per vertex, we're also going to send a vertex color. So we can have different colors on each vertex, or maybe all the colors will be the same, that's fine, but it just gives us a way to pass in the color. And to do that, what we're going to do is use interleaved vertex data. So let's actually go to our sprite class. Here we go. So in our sprite class, here's where we set up our vertices. Now you'll notice we have the positions in this float array of 12 floats, 2 for each vertex because we have 6 vertices. Now we could also have another array for colors, but that is not the most efficient way to do it. The actual efficient way to do this is to do what's called interleaving our vertex data. And what that means is basically each vertex is a struct that has the position, the color, and everything, and then you have an array of instances of this struct. So let's go ahead and create ourselves a header file that's going to hold our vertex definition. So we're going to add a new item, sorry, and then we're going to go to header here, and it's going to be, we'll call it just vertex.h, very simple. Vertex.h. So now if we go in vertex.h, we're going to do pragma once, and here's where we're going to put our vertex struct. Now we don't need a CPP file because this vertex struct isn't going to have any methods, it's just going to be data. So we're going to say struct vertex, like that. Make sure you have your semicolon there at the end. And then, okay, so what does it need? Well, it needs a position. So we're going to say float position, and it's 3 floats, or 2 floats. I keep forgetting we're in 2 dimensions. And then we also need color. Now, color could also be floats. However, that's going to be a waste. So if we say float color, and we'll say 3 floats for red, green, and blue, this is going to be 12 bytes. However, we don't need 12 bytes of color. If we open up Paint, and I had some weird stuff over here. If I pick up a color here and look at it and hit edit colors, you'll notice the red, green, and blue values down here are numbers between 0 and 255. When I move this, they're only going to be numbers between 0 and 255, nothing in between. They're just little integer numbers. And 0 and 255, if you remember, that is a number that can be held in an unsigned char. So an unsigned char is just a single byte instead of 4 bytes. And it's always a good idea to make your vertex structs as small as possible because it basically makes the transfer to the GPU much faster. So instead of having a float color, we're going to use an unsigned char color. So we'll say unsigned char color 3, like that. And we can also, if we don't want to type unsigned char, we can include gl glue here, glue.h, and from this we can use the type def glu byte. And this is the same thing as an unsigned char. It's guaranteed to be 1 byte. So here we have a 3 color array of bytes. So our red, green, and blue will be a number between 0 and 255. However, this is actually not good because right now our actual vertex struct, if we calculate the size, we're going to get 2 floats, which is 8 bytes, and then 3 bytes. So 3 bytes plus 8 bytes equals 11 bytes. But that's not what you want. You want your vertex struct to be a multiple of 4 bytes for alignment issues. It just makes it better. So what we're going to do is add an extra byte, GLU byte, padding like that. And if you add an extra byte of padding, now it's going to be properly a multiple of 4 bytes like that. But instead of doing it there, what I'm going to do is just make it a 4-component color array. So we'll have red, green, blue, and alpha. And if you're not familiar with alpha, that is transparency. So it's basically how much you can see through something. And we're probably not really going to use alpha. We're just going to like set it to a 255 or something like that. So there is our vertex struct. Now when we go to sprite, instead of having 12 floats, we're going to have 12 vertices. So let's go ahead and include vertex up here, and then instead of 12 floats, we're just going to say vertex data 12. So we have 12 vertices, and actually it's not 12 vertices, it's 6 vertices because the positions are already stored in each vertex. There's 2 positions in each vertex. So now what we need to do is change the way we set this up. So since we are doing, we'll say, let's just change these to do the position right now, and then we'll worry about the color. We're just going to say vertex data dot position, vertex data 0 dot position 0, like that. So the first vertex, its position 0, which is the x position, equals x plus width. And let me zoom in here in case you can't see. Now we need to set the y position. So we're going to do the first vertex again because we need to set its y position. We're going to say position 0 equals y plus height. Well, it's kind of weird to say 0 and 1, oops, there we go, 0 and 1 for x and y. Wouldn't it be convenient if we could say dot x and dot y? Wouldn't that be better? Well, actually, we can do that. We can do something clever. So if we go to our vertex struct, what we can do is do a little composition. We can create our own struct inside vertex struct that will be our position struct. So we can say struct position like this, and then inside the struct position, we can say position dot, we'll capitalize this position right here. We can say, sorry, not position dot, we can say float x and float y. And then before this semicolon here at the end, we're going to actually name it, and we're going to name it lowercase position. So what this is doing is it's making a struct called, a struct of type position, and it's creating it, and then it's creating an instance of it called lowercase position. So now we don't need this float to position. Instead, we can say vertex dot position dot x. And we can do the same thing with color. Let's do the same thing with color. Let's say struct color, and we're going to say float, or sorry, GLU byte R, GLU byte G, GLU byte B, GLU byte A for RGBA for red, green, blue, alpha. And then we'll call this lowercase color, like that. So then we can get rid of that. So now our vertex is a lot easier to work with. It makes a lot more sense intuitively. If we go to our sprite.cpp, instead of saying position 0, we can just say position.x and position.y. And it's just as easy as that. So now we need to do the other vertices. So 1, 2, 3, 4, 5. So 0 through 5, there we go. And then we can just copy this dot position dot x for all of these, and then dot position dot y for all of these. And so when I created a struct inside our vertex struct, that's called composition. You're basically storing a struct inside a struct, and you can do the same thing with classes. So there's our position. Now let's actually set our colors. So for color, what I'm going to do is just set all of the colors equal to the same thing for now. So I'm going to use a for loop. So for int I equals 0, I is less than vertex, or actually is less than 6, since we just have 6 vertices, I++. What we're going to do is say vertex data I.color.r equals, so the red color, let's say, is 255. And let's go ahead and copy this. For the green color, let's say 0. For the blue color, let's say 255. So this will make it magenta. And then for alpha color, we're also going to say 255. That'll make sure that it's not transparent so that we can actually see it. So there we go. That's going to set up our vertex positions and our vertex colors with our composition so that it's easier to figure out what these actual values are. And now what we need to do is, so we're uploading the buffer exactly the same. We're doing size of vertex data, which is good. That's what we want to do. Since this is a static array, size of is correct. That will give us the correct size. If it wasn't a static array, we would have to do something like size of vertex times 6 or something like that. But since it's a static array, this works just fine. So that will upload our buffer data. Now there's another thing we need to do. We need to go into our color shading vertex shader and actually make it so that it uses the color. So let's do in vec4 vertex color. And that's it. So remember, vec4 means 4 floating point numbers. So it's like an array of 4 floats, just like our color array is, except our color array is bytes, not floats. But that's actually okay. What's going to happen is when we pass in the bytes to OpenGL, what it's going to do is it's going to convert them into floats before our graphics card uses them. So everything works out just fine. So now we have our in vec4 vertex color. What we need to do is actually pass this to the fragment shader so that we can use it here instead of setting the color to red on our own. So in order to pass it to the fragment shader, all you do is use an output. Just like we have an output from the fragment shader, this out vec3 color, we can have an output from the vertex shader. We just need to make sure that they are named the same thing between the two stages. So what we can do is say out vec4, and we'll just say capital color, something like that. So out, actually let's call it fragment color. That's a good name for it because we're sending it to the fragment shader. And what's going to happen is, remember, it's going to get interpolated. So if we have different colors per vertex, they're all going to get mixed together. And then in the fragment shader, right here, it's going to use the mixed color. So let's go ahead and have our input here, and we need to make sure it matches vec4 fragment color exactly. So we're going to say, instead of out vec4, we're going to say in vec4 fragment color. And make sure you save it. So now we are correctly passing the fragment color out from vertex shader into the fragment shader. So let's go ahead and set that variable. We have to be sure to set it. So all we got to do is at the end of void main in the vertex shader is we say fragment color equals vertex color. Very, very simple. So we'll save that, go to fragment shader. And now instead of color equals vec3 of these components, what we're going to do is say color equals fragment color. Now if we just wanted to send out 3 components of the color, we could say .rgb to send out a vec3. But what we want to do is, since we have the alpha, we might as well send the alpha as well. So if we change this vec3 color to a vec4 color, it will take into account the alpha, which for us it's going to be 1, so nothing is going to change anyways. So that's that. That's the only change we need to do right now to our shaders. So let's go ahead and set up our vertex attribute pointers. So if we go to sprite : draw, you'll notice we are setting up this vertex attribute pointer right here for 0 and then 2 floats. Remember, this is our position. So let's go ahead and say this is the position attribute pointer. Now we also need a color attribute pointer, but what we need to do is, since we're using interleaved vertex data, we need to actually change how this works a little bit. So this GL false right here is normalized. That's going to stay false. That's what we want. After GL false, we have what's called GL size I stride. And what the stride is it's the size of your vertex struct. If you're not just using just the two floats, which now we're not using the two floats anymore. Now we actually have a vertex struct that has other data in it. So we need to set this stride variable. And the way we do that is we just say what the size of a vertex is. So all we're doing is saying size of vertex, like that. Very, very simple. And then this constant void pointer is actually going to be the offset in bytes of the position inside our vertex struct. So our position is at the beginning of the vertex struct, so it is a 0-byte offset. It's very simple. So it's just going to be 0. However, our color is not a 0-byte offset because there's a position before it. There's 8 bytes of position before the color. So when we set up the color pointer, we need to set it to an 8 for 8 bytes after the beginning of the vertex struct. So let's go ahead and go to Sprite and do that. So we can put a 0 here, but a more proper way to do this is to use the offset of. And actually offset of, I don't remember where it is. Let me pause the video real quick. Okay, so the header file we need to include to get offset of is include cstd-def. And that is the header file that has it. So now we can actually use it. What we can do is type offset of, and then we're going to type vertex because we're using the vertex struct, and then we need to type position because that's the variable we want to calculate the offset of. Now this is going to just return a 0. It's very simple. We could have done the calculation ourselves, but this is the more accurate way to do it because when we use offset of, if we ever change our vertex definitions, we don't have to remember to come here and fix the number. Now this is giving us an error. It says size t is incompatible with type void star. It wants us to pass in this last parameter as a void star, which means basically just a pointer. Just a generic pointer. So we're just going to do that. We're just going to cast it to a void star like that. So we just type void star in front, and that makes it a-okay. So there is our position pointer. Now we need to do the color pointer. So vertex attrib pointer, I'm just going to copy paste that, and we'll say this is the color attribute pointer. So now the first argument is the index. This is going to be 1. So position was an index of 0, color is an index of 1. Next, it's the size. So how many variables are there? And there's going to be 4 bytes, so we're going to type up 4 here. Next is the type, and we are using unsigned bytes. So the macro for this is gl unsigned byte, like that. Next, it's asking if we want it to normalize, and in this case, we actually do. What normalize means is it means to convert it to a range between 0 and 1. So right now, our numbers are between 0 and 255. However, if you remember, in our vertex shader, in our fragment shader, the color that we output is a number between 0 and 1. So all we have to do is set true, and then what it's going to do is convert anything in the range 0 to 255 for our fragment color to the range 0 to 1, and that's exactly what we want to do. So we're going to say GL true. Next, we do the stride, which is the same thing, just size of vertex. And then finally, a pointer to the offset, and we do the same thing. We're going to do void star. We're going to type offset of, and we're going to use the vertex struct, and we're going to find the offset of color, which is going to return an 8, since it's 8 bytes after the beginning because of the positions. So there we go, that sets up our vertex attribute pointers. Now there's only one more thing we need to do. We need to actually, in our GLSL program, we need to add that attribute. So let's go to, I believe we did it in main game in the, here we are in the init shaders. So we did add attribute vertex position. Now we just needed to do add attribute vertex color. Just like that. So let's go ahead and run it. And we should get something pretty cool. There we go. It is now purple. Now let's see what happens if we do different colors for each vertex. So let's go back to, where did we do this? In sprite.cpp. So here I set all the colors. I'm going to leave that. And then after I set all the colors to magenta, I'm going to change a few of the colors. So let's change vertex 1, which is the top left-hand corner. Let's change that one. So we're going to say vertex data, and let's say, we're going to say 1.color.r equals, and we'll say 0. And I'm just going to copy this and change the I to a 1. So we'll say the top left corner is going to be blue. And then let's make the bottom right-hand corner, which is vertex data 4, let's make that one green. So I'm just going to change this to a 255, and I'm going to change this number to a 4. So there we go. The top left should be blue and the bottom right should be green and the rest should be magenta. And look at that, we get this really cool color gradient. This is that interpolation I was talking about. So each pixel, since it's using the input from the vertex shader, this fragment color right here, it's going to get interpolated between. It's going to figure out what color it should be based on the colors of the surrounding vertices. Now, what if we don't want it to do interpolation? We can actually stop it from doing that. Instead of out vec4 fragment color, we can say flat out vec4 fragment color, and this will stop it from doing interpolation. So let's see what that looks like. We have to match it on both sides. We have to say flat in vec4 fragment color in the fragment shader. So let's restart here. Let's go ahead and run it. And there we go. Now it's solid magenta. It just ignores some of the vertices, and in this case it was ignoring the top left and the bottom right hand colors. It could be something else. I think it's pretty arbitrary, but we want to interpolate it because that looks really cool. So let's go ahead and change that back and run it one more time. And that just looks so cool. Now, if we wanted this to change color, we could change this color every frame and keep re-uploading our buffer, but there's other cool things we can do with what are called uniform variables, which we are going to learn in the next tutorial. So be sure to stay tuned, and I'll see you in the next one.